We have discussed many properties of light. Our discussion evolved from how light propagates to how it interacts with matter on both the macroscopic and microscopic scale. Now we shall use all these properties to discuss the scattering of light in solar cells. Light scattering is well illustrated by this bank of thick fog crawling over the treetops. The fog is bright white, but there is no apparent source for this illumination. We know, of course, that the sun is responsible for Earth's illumination. In a thick fog, however, all the sun's direct radiation is scattered by the many water particles. This causes the light to reach an observer from many directions rather than just the sun's direction. The scattering of light is not a separate event from those interactions we discussed so far. Scattering rather encompasses all those events to describe a process where a light beam is deflected from a straight path. Scattering can therefore occur through reflection, refraction, or diffraction. Scattering can even occur through the absorption and subsequent re-emission of a photon. This type of scattering is known as Raman scattering and is often used in material research. Scattering is an important part of light management in solar cells. In this video we will learn what exactly light scattering is. We will learn about the different scattering regimes and when each is valid. We will identify the differences between Rayleigh and Mie scattering. Finally, we will discuss how the differences between the scattering regimes can be applied to further improve the performance of our solar cells. From a foggy sky to a clear blue sky. This picture of a bright white sun set against a clear blue sky is familiar to most of us. This picture does, however, raise some questions. Why does the sky appear blue and the sun bright white? And on the same note, why does the sun appear red when it's rising or setting? The short answer is wavelength-dependent scattering. A more complete answer, however, involves the relation between a wavelength of light and the size of the particles it encounters. If the product of the refractive index and the diameter of a particle is much smaller than the wavelength of a photon, a type of scattering takes place that is known as Rayleigh scattering. However, if the refractive index diameter product is of the same order of magnitude as the photon wavelength, then we enter the domain of Mie scattering. Macroscopic scattering occurs for particles much larger than the wavelength. Macroscopic scattering involves the refraction and reflection we discussed earlier in this section. We will first look into Rayleigh scattering. The shown equation is used to describe the light intensity at a certain angle after a light-particle interaction. The angular intensity distribution depends on the refractive indices of the particle and surrounding medium, on the wavelength of the light, on the particle diameter, and the distance to the particle. The angular intensity distribution of a Rayleigh scattered light wave takes the form of the shown figure. As much of the light is scattered in the forward direction, towards 0 degrees, as in the 180 degrees backward direction, we can also observe that light is scattered into all outgoing directions, if not equally. Furthermore, we can gather from the first part of the equation that Rayleigh scattering is strongly wavelength dependent. The intensity scattered towards a certain angle depends on 1 over the wavelength to the power 4. This strong wavelength dependence of the scattering intensity is visualized by the shown graph. The y-axis or vertical axis shows the scattered intensity at a certain wavelength divided by the scatter intensity at the same angle at the wavelength of 250 nanometer. We can see the particles with a diameter much smaller than the wavelength of visible light are very effective at scattering blue light. It happens to be the case that the air in our atmosphere is full of Rayleigh-sized particles like oxygen and nitrogen. This figure demonstrates why the sky is blue. Imagine we are the observer on the ground. Light from the sun that directly reaches our eyes contains all wavelengths in the visible spectrum and therefore appears white. From all other angles, we can only observe light that is scattered by the particles in our atmosphere. As we can see in the figure, a fraction of a solar ray is scattered in our direction every time a light wave interacts with a Rayleigh-sized particle in the atmosphere. Furthermore, as we observed from the graph, blue light is scattered most effectively. Therefore, from all directions in the sky, the intensity of blue light that reaches our eyes is dominant. Hence, the sky appears blue. But what about larger particles? Gustav Mie first derived the solutions to the Maxwell equations, where the particle size is of the same order of magnitude as the photon wavelength. Mie scattering is much less dependent on the wavelength and therefore scatters blue and red light about as effectively. We can gather that, unlike Rayleigh scattering, Mie scattering occurs mainly in the forward directions. The angular distribution thus depends strongly on the particle size. The figure shows the angular distribution of 3 increasing particle sizes. On the left is a particle with a Rayleigh distribution. In the middle a Mie distribution, while on the right side a Mie distribution with an even larger particle. Increasing the particle size even further would lead to a straight line, as dictated by the Fresnel equations. The mainly forward direction of Mie scattering influences our perception of the sun as it rises or sets. When we see the sun setting in the evening or rising in the morning, the sun appears low on the horizon. Because of this angle between the sun and our position on Earth, light has to travel a larger distance through our atmosphere than during daytime. This means that light encounters more particles in the air and more scattering events take place. With every scattering event, the intensity of light is distributed. Therefore, the many Rayleigh scattering events cause the blue light from the sun to be fully scattered. The intensity of blue light reaching our eyes is therefore so low that it is no longer observable. Red light also undergoes an increased number of scattering events at the sunset. For Mie scattering, the angular distribution is mainly pointed in the forward direction. Mie scattering therefore does not cause red light to be fully diffused. The different scattering properties of red and blue light are taken into account during solar cell design. An example thereof can be found in a multi-junction solar cell, which is a solar cell consisting of multiple PN or PIN junctions stacked on top of one another. In this multi-junction thin film silicon solar cell, incident light first encounters a high bandgap amorphous silicon absorber layer, responsible for the blue light absorption. Red light is transmitted through this layer and absorbed in a second nanocrystalline silicon absorber layer with a lower bandgap energy. With these functions in mind, the interface in front of the amorphous silicon layer has very small Rayleigh-sized features. These features effectively scatter the blue light, but hardly affect the red light. The nanocrystalline silicon texturing, on the other hand, has larger features to effectively scatter the incident red light. Now, in summary, we saw how Rayleigh scattering occurs for particle sizes smaller than the photon wavelength. When the particles in a photon wavelength are of roughly equal size, Mie scattering occurs. In the case of Rayleigh scattering, light is effectively scattered in all directions, and Rayleigh-sized particles are very effective at scattering small wavelength photons. This is why the skies appear blue. We discussed how Mie scattering, on the other hand, is less wavelength dependent and therefore scatters all visible wavelengths more or less equally. Mie scattering occurs predominantly in the forward direction, which explains why a setting and rising sun appears red. Finally, we discussed how texturing features with different sizes can be used to effectively scatter different parts of the spectrum. I'll see you again in the next video.